Hello students, welcome back to another lecture on classical electrodynamics, and today we have lecture number 23. In the last few lectures we have discussed the potential formulation in electrodynamics, which means that we have obtained the equations for the electromagnetic potentials, and we have seen that under the Lorentz gauge both the equations happens to be the wave equation, and that's what I'm showing here. Of course, for remembering what happened in the last class, these are the two equations we have derived. The first equation being the one for the electric potential, and another one for the magnetic potential. So we should not use the word static. Okay, we should not say electrostatic potential, we should not say magnetostatic potential, but rather we say electric and magnetic potential, or even better, electromagnetic potentials, because now all of them are actually space as well as time dependent. And the only thing that is very good thing is that the appearance of the equation is in the standard wave equation, and therefore we have a solution technique for obtaining the solution for all of them. This is one thing. The second thing is, the interesting point to be observed is, as you can see, the next set of equations that I have written in the yellow color is once again the wave equations in terms of the electric and magnetic field. And this you already know, of course, from your undergraduate study, that starting from the Maxwell's equations, you can always obtain the electromagnetic wave equation. You have two curl equations, right? You take the curl of the curl equation, then you will be getting the wave equation. So of course that part is quite familiar to you. So I am now writing in order to compare and then see that once again in the case of the field, okay, the yellow color equations that I have written is the wave equation for field, whereas the white color equations are the wave equation for the potential. So ultimately what is interesting here is that whether you take the potential equations or the wave equation, you finally have the wave equation, and therefore if you know how to solve a scalar wave equation, then you can solve all of them together. Together means, okay, they are independent of each other. That is another interesting point. Now the coupling itself is not there, okay, which means that coupling is not there means when you have the phi electric potential, this phi doesn't appear in the case of the second equation for the potential. So therefore you can solve the electric potential independent of the magnetic potential, and similarly you can solve the three components of the magnetic potential independent of one another. And similarly, and so is the case for the yellow color equation, you can solve for the x component, y, z components of the electric and magnetic fields independent of each other. So the one doesn't depend on the other directly, all of them being independent. So we have an uncoupled set of equations, and therefore this is an added advantage. Now the point to be noted from the wave propagation equation is that you have the second derivative in time. So a differential equation that is second derivative in time is not characteristic for a dynamical system. Okay, it is rather characteristic feature of wave phenomena. So when you have the first order derivative in the differential equation, then generally they represent the time evolution of a dynamical system. So you can have different varieties of electromagnetic phenomena. Okay, you cannot say that each and every electromagnetic phenomena is a wave phenomena. It is not so. Okay, if you want to have a wave phenomena, then your physical system should be so. Okay, which means that you should have the second derivative mathematically, and physically it represents wave phenomena, which means that the electromagnetic radiation is present. Only if the radiation is present, there will be a wave phenomenon for the propagation of the energy. But if you don't have, if you don't have the second derivative in time, one second. So provided that you have the second derivative in mathematically speaking, then that would represent to a physical system where radiation is taking place. So in this case electromagnetic radiation, and therefore the radiation propagates. So we have a wave propagation phenomena corresponding to the second order time derivative. if you have a first order time derivative, for example, in the case of Faraday's experiment that you are going to do, you are not going to have the radiation process. So that will represent the dynamical system. So depending on the physics that you are going to have, or kind of experimental setup that you are going to have, you can have both the first order time derivative representing a dynamical system, or a second order time derivative system, which means physically it represents the wave propagation of radiation. So this is the idea that we are going to get from the appearance of the Maxwell's equation and rewriting the Maxwell equation in terms of potential, and once again the wave equation from the field. Now what is interesting is that once you understand, or once you realize that the second time derivative representing the wave propagation phenomena, it is quite clear that the energy is going to propagate. Okay, wave is propagating means what is going to propagate? The electric and magnetic fields is going to propagate, and which means that it is very clear that energy is going to propagate. So that is one thing. Second thing is that it is quite clear from this expression. You have 1 over c square appearing in the electromagnetic wave equation. So it clearly tells you that the propagation speed of the electric and magnetic fields would be at the speed of light for vacuum, of course. Okay, since all the discussion that we have seen correspond to the vacuum, automatically the wave propagation phenomena is to be considered in vacuum. Okay, for non-vacuum system you can always modify the equations, but that we will see later. So right now the 1 over c square coming into picture is clearly indicating that the speed at which the electromagnetic information, the speed at which the electromagnetic information is propagating is same as the speed of the light itself. So which means that you can at least visualize that if you have an electric bulb in your in an open space, for example, okay, you don't have boundaries like walls. Okay, you don't have any wall, you have an electric bulb in an open space, and assume that the light is glowing. And suppose when it is glowing, what is the meaning is that the electromagnetic wave is now propagating, and this is the information. Now this particular equation is the one which is giving the evidence that light itself is an electromagnetic radiation. Otherwise, that this concept is quite familiar to you. The fact that the light itself is electromagnetic radiation comes from this equation. This is the equation that gives you connection between the speed of the light and the mu naught and the epsilon 0. So you have the relation between the speed of light c and the mu naught epsilon naught. So that connection is the one which provides evidence that light is electromagnetic radiation, and electromagnetic radiation will propagate with the speed of light. So that connectivity came from this equation only. So that is the reason why we can now consider an example of an electric bulb. And if you are going to consider in some kind of a space where you don't have boundaries, and if the light is glowing, it means that the electromagnetic radiation is propagating. So the moment you switch off the light, so what happens is that you are not going to get the source of radiation. So once the source of radiation is not there, the meaning, or what is that you have to understand, is that the radiation what was there before switching off, that continues to propagate. That will not stop. So that is propagating, and it is going away from you at the speed of light. Which means that since the light is propagating away from you, you finally feel the darkness. Okay, you assume that there is only one light source and nothing else is there in the complete dark. Okay, in the midnight, and if the only one light source is there, so if you switch off that, why do you feel the darkness? Is that the radiation, electromagnetic radiation that was originating from the electric bulb, it propagates away from you, assuming that you are holding the bulb. So that is how you assume. So since it is receding away from you, so therefore you completely see the darkness. And what why do you want to take this kind of an example is that we would like to consider what is the energy that is going to propagate per second. So every second the energy is going to propagate, because we are talking about the speed, right? Speed of light means what? There is a speed. Speed means per second you have to talk. So therefore, what is getting propagated from one place to the other is the energy. And where from the energy came is, energy is coming from the electric field and magnetic field. Electric field is a source of energy. Magnetic field is a source of energy. So electric and magnetic fields together, when they move or when it is propagating, we say that the energy is transported from one place to the other at the speed of light. And therefore the question comes, how much amount of the energy is transmitted from one place to the other per second, right? So therefore this can be visualized. Of course, I would like to show this. For example, I would like to show one example. So here, this is the scenario that I was talking about, the presence of an electric bulb that was glowing. So when it is glowing, you feel the light being illuminated all around you. Now the point that we are interested is all around you means you'll have to consider a sphere of some radius. Because the light is going to propagate in all possible direction with identical speed, okay, in all direction in identical speed, that means in whether it is in the north direction or in the east direction, the speed of light is going to be the same. Because of that reason only we have a sphere. Okay, otherwise we can consider a rectangular box as your surrounding region. Okay, so the reason is that surrounding you in all possible direction, the speed of the light is going to be same, and therefore after 1 second, for example, then the light would have propagated up to this point, which is the boundary of the sphere. So now the point is that if you are going to switch off the light, then what happens is the center point is the place where the bulb is present and which is glowing. And if you're going to switch off that, then this electric or electromagnetic radiation, whatever it is, the light that is present, it will continue to propagate. Okay, just because you stop or you switch off the light, this radiation will not stop. So this radiation will keep propagating at the same speed of light away from you. Okay, and therefore you will feel the darkness surrounding you. So that is what is quite familiar experience, but we would like to have this so that we are going to write down some expressions corresponding to that. So let me therefore see this. Let us observe how the darkness is coming. So once you switch off, you feel the darkness surrounding you because the light that was present in this particular region is propagating away from you, and ultimately you see the darkness there. So this concept is quite clear, and from here what is that point that you are going to understand is, the point that you understood is that energy is leaving the place with the time. Okay, the energy is in the form of electromagnetic energy, and once it is having the the wave propagation phenomena, then the energy will be transported from one place to the other. That's important. If you are not going to have any kind of radiation phenomena, okay, in your experiment, then energy is not going to propagate like that. But instead of that, the energy will be stored locally in the region where you are going to consider the experiment. So this point is once again very important. The point that I am trying to say is that if you are going to conduct an experiment with a parallel plate capacitor, for example, then the space between the plates of the capacitor will be filled with electric field. And if you are going to insert a dielectric, of course the electric field strength will be multiplied by this epsilon r, and therefore the energy density will be increased. So energy is of course stored in between the space between the parallel plates, and you are going to increase that energy density by adding some dielectrics. But ultimately the point to be noted is that energy is not going to propagate. It will be storing there. So it is up to you what kind of experiment that you are going to conduct. If you are going to conduct an experiment with electromagnetic radiation, then wave phenomena is going to take place, and therefore the energy will be transported from one place to the other with the speed of light. And of course the speed of light can be slightly affected if you are going to consider some material medium. For air or for the case of the vacuum, the speed is going to be fixed as the speed of light. That is the point. So the conclusion is therefore clear, right? The energy will be propagating only if you have a wave phenomena. If you are going to have a kind of a solenoidal setup, for example, or a toroid, okay, where you are going to wind the wire around a particular cylinder, and when the current is flowing, depending on whether it is steady current or unsteady current, you'll be having the magnetic field, which is a steady magnetic field, or it could be a time varying magnetic field in your local region. Local region means, for example, if you are going to consider an electromagnet, then the magnetic field will be present only between the poles of the magnet. So poles of the magnet mean was behind the poles you are having the windings, and the inside in the winding you have the current is flowing, and therefore you are basically establishing a magnetic field in a solenoid kind of setup. That is called electromagnet. And therefore you can have magnetic field, you can have electric field locally in the experimental setup, which will not propagate, not necessary to propagate. So whether it has to propagate or not, that depends on the kind of experimental setup that you are going to have, and the corresponding mathematical equations will represent the first order time derivative or the second order time derivative. So that's the point to be considered. So once no, so you are going to decide right now. So what is that we are going to consider in today's class is that let us consider the wave phenomenon, in which case it is very clear that we have seen that the energy is going to propagate in all directions with identical speed, and therefore we can always consider a sphere of radius r, whatever be the radius, that's okay, but you have to consider a spherical surface, not a rectangular box or a cubical box. That kind of a box is not possible because the light speed is going to be identically same in all possible directions. So once this point is clear, we would like to make some calculations. That is what I am trying to show, that if this is the case, once you understand that the energy is leaving the place with respect to the time, the question is therefore, it is clear that we need to ask, or we need to know how much amount of the energy is flowing. Now, in order to do this calculation, let us start with something which is quite simple, and we can quickly modify that particular expression to the required situation. So you take the case from the very basic circuits, electrical circuit, where you say that the voltage multiplied by the current in a circuit is the power. And why do you want to consider this? Power is the joules per second, isn't it? That is the reason why we are going to consider. And if you are going to write the dimensions, we can write like this. So you have the voltage, that is the potential difference multiplied by the current, that is equal to the power in an electrical circuit. And power is nothing but the energy per second. That is what we are talking about. Some energy is there which is going to propagate, but in the case of the electrical circuit, it will not propagate in space, but it will be within the circuit itself. But whatever be the case, the energy is flowing in the circuit. So the difference between this equation and the radiation example is, in this example, the energy will be flowing in the circuit. In the radiation example, the energy is flowing in the space, free space. Okay, but whatever be the case, the identical expressions are, in fact, we can consider, and therefore we can write like this. So let us try to modify this particular equation slightly. What I am going to do is that I am going to I am interested to bring somehow the electric field and magnetic field into the discussion. This is the one corresponding to the electrical circuit where you have potential difference and current. But in electromagnetic theory, we have the electric field and magnetic field. So somehow you have to convert them or modify, or you have to manipulate this and bring the electric and magnetic field. So for that, what I do is, I know that the dimensions of electric field is volt per meter. That is why I am trying to write voltage as volt per meter, and that meter I can multiply. So I am essentially dividing by meter and multiplying by meter. And similarly, this is a current. So current per unit area is what is known as the current density. And the current density, capital J, is present in the Maxwell's equation. And therefore, I would like to bring the current density into the equation. And therefore, I will write down like this. It is the ampere divided by meter square. Then what happens is you can multiply by meter cube. So because you divided by meter square, in order to compensate, I put a meter cube here so that I'll get back the original expression, and therefore this equality is satisfied. So the purpose is therefore clear, that this quantity becomes electric field, this quantity becomes current density, and both of them are present in the Maxwell equation, and therefore somehow I can manage to discuss the electromagnetic wave, and then on the left hand side I have the energy per unit time. So this is the idea behind this kind of manipulation. And once this is clear, now let us write down that this is nothing but the dimensions of the electric field, and then the square bracket is actually dimension, that's all about it. And then this is for the energy density, then you have a volume. On the left hand side, of course, you have the energy per unit time. So whether you write energy divided by time or in terms of English sentence, this will be written as energy per unit time. So I would like to write down that. So energy per unit time means divided by time. So that is the quantity. So this is how we understand certain things basically. But however, there is a point to be noted here. So this is not a mathematical expression. This is not an expression. This is to understand the dimensionalities or dimensions of physical quantities. So somehow we are now happy to say that energy per unit time can be written in terms of electric field and current density. That is the meaning. The square bracket represent the dimension of electric field, not E itself. If it is E itself, then the problem will come. What problem will come is, this is a vector quantity, this is a vector quantity. And when you have two vector quantities, you have to clearly tell whether you have a dot product or cross product. So that is the reason why the square bracket is there, means square bracket represent dimensions, that means volt per meter. So you don't have to worry about what kind of product it is. It's a simple multiplication. So therefore, now let us write down a proper mathematical expression based on this kind of dimensional analysis. And when you are going to write down a proper expression, you understand one thing, that energy is a scalar quantity. So I have to obtain the scalar quantity based on two vector quantities. These two are vector quantities. So the only way to obtain the scalar is that you take the dot product. If I take a cross product, you will get a vector quantity, but energy is not a vector. Therefore, the only option for you is to put a dot there. So based on this idea, we will write down that I have an electric field vector. I'll write down E vector, then dot J vector. So that would be clear. The volume, I would like to write down some kind of a d omega, and so that I can perform the integration. So the integral of the elemental volume, whether it is elemental volume or the total volume, whatever be the case, they will have the dimensions of meter cube. So that part will be taken care. Now, if you are going to integrate this kind of expression, then we will be putting a d omega and then integrate it here. That's the meaning, and therefore the correspondingly on the left hand side it will remain the same, nothing will happen. But since we are writing in terms of an equation, let us write down this as dw by dt, in the sense that what is this w coming into picture is, usually from mechanics we have the habit of saying work done. Work done is usually having the dimensions of energy. Therefore we say that it is the amount of the work done per unit time, or we say that the rate of work done. So per unit time is what, when you write down d by dt, we say that it is the rate of work done. So this is how you can write down mathematically. But then this is fine. But then the question is that this is not looking like a proper proof or kind of a good derivation. It looks nice, and we feel quite comfortable because we have obtained from an elementary circuit analysis, and then based on the dimensional analysis we have established this. But the moment you write down the work done here, the question naturally comes, for the case of the electromagnetic phenomena, whether the work done is really the expression given by E dot J. So that kind of general doubt may arise, and therefore let us make it clear by drawing a diagram, and then I'll show that. Okay, so now that the W is work done, that is, you keep it here. So what I'm trying to do now is that I would like to draw a particular diagram and then show that work done can be written down as E dot J itself. So I'll go to a different board. And then show that. So here, what is the purpose of this kind of a diagram here is that in some region of space, so in the integration we have written d omega. So d omega means elemental volume. Elemental volume means a small volume in this particular region. Now this is a three-dimensional region, where some electric field and magnetic field is present. So the blue color region, which is shown in some kind of a shade here, represent some kind of field. Some kind of field means a combination of electric and magnetic field is present in the system. That means in this particular region, don't have to worry about what is the direction. There is some direction, of course. Electric field and magnetic field is present means direction is automatically there. So both of them are present, and since the shade is not identical, you see that the blue color here in this boundary and the blue color here is not identically same, isn't it? So that means the what is that indication is that the strength of the field is not uniform. So you are not going to have a constant electric field, you are not going to have a constant magnetic field. So the point that is to be noted is that you have some kind of an electric and magnetic fields, not necessarily constant field. That is the meaning of the different shades that are there in the system. Okay, that is one thing. Now in addition to that, we are going to have a collection of charges. Now a collection of charges is what is known as charge density. Now what will happen? Now you ask the question, you are going to have a collection of charges, and then surrounding this region you have an externally applied electric and magnetic field. So the point should be clear. Point is, we are applying some electric and magnetic field externally. Okay, from how did you generate that field? That is no, you don't have to worry. You are generating somehow and then applying that field here. So this should not be confused with what is the electric field generated with these charges. That is not the question. So this point should be clear to you. These charges will generate some electric field, that you forget. We are not asking about that and we are not interested in that. Now the question is different question. We are going to apply some electric field together with some magnetic field in some region of space using some apparatus. So in that region is filled with electromagnetic field. Now in that place we are going to keep a collection of charges and what we call by the name charge density. The question is whether the charge density or the collection of charges will remain at the same place or will it move. That is the question. And the answer is that the Lorentz force law will tell whether it will move or not. So you know what is Lorentz force law? You know that Q into E plus whatever is there for the magnetic field. So certainly Q into electric field, that is the force. Now once you have a force, it has to move. Dynamics is there, so certainly it will move. That's the point. In which direction will move, and all these things depend on the strength of the field, the direction of the field. So once you understand that it is going to move like this, then you can ask the question that there is a displacement when the charges are moving. When the charges are moving by some kind of a length, say dl, then we say that is a displacement. Okay, and then you have the force. What is the force? Lorentz force is there. So therefore the force is there which is acted on the charges, so that will be the F. And then if these charges are moving a little bit, say dl, then F dot dl will tell you the work done. So therefore work done is possible in an electromagnetic system. So that is the point that I am trying to explain. And if you are going to write down the equation, of course it is quite simple. So let us therefore write down an equation corresponding to the work done. That's what I have written here. The F means the Lorentz force that we are going to write down, and therefore dW is the work done, which is equal to F dot dl. So once these things are clear, let us therefore write down. I will first of all write down the Lorentz force law, and then we'll come back to this. V cross B, right? That's all about it. And put some kind of proper bracket. It's not coming. So that quantity dot dl vector. And let us explicitly write down for each term electric field. So now what I am trying to do is that let us write down this as V dt. Now you can understand what is this dl. So dl means the small displacement of the electrons, let us say charges. So charges is moving by small distance. Now it has moved over some time, right? So whether you are going to have the charges moving, not moving, whatever be the case, time will change, right? So the electrons has moved a little distance means when the electrons are moving, by that time some time has changed, right? So that time is dt. So that is the time during which the electrons have moved. And since the velocity of the electron is there here, so when you multiply the velocity multiplied by the time, that combination, v times dt is equal to the dl. So we are actually rewriting this particular dl into velocity into time. That is because time is an independent variable, so you measure it, and then velocity is the one that you may be measuring or you may be calculating. So therefore, rather than having the length vector here, we write in terms of velocity and time. And similarly, for the second term, we can write down so that you can see what is happening. So the purpose is clear. No, only when you write this, it appears that something can be simplified. So now we are able to simplify this quite easily, because you can apply the simple, the vector algebra rule. We will write down this expression. So that is the standard vector algebra, and you can see what happens to the a dot b cross c. So this is a, this is b, this is c. So based on this expression, what happens is there is a v here, there is a v here. So these two things are identical v, same, right? And therefore what happens is when two of the vectors are equal, when two of the vectors are identically same, then the cross product will give you 0, right? And that is the reason why the second term goes to 0. So that means when you are going to convert this length into the v times dt, we are able to simplify, and therefore I will now write down that particular information, that it goes to 0. So once that is 0, we are left out with only one term. Therefore, I can write down that dw by dt equal to q times E dot v. So that is the only information, or that is the only term that is surviving now. The reason is that this particular dt, I have brought it down here to the left hand side, and that is why you have q times E into v. Of course, I would like to say that where is E and B are present, I already explained, but just I am writing now that the electric and magnetic field is present in the shaded region. Because when you write here E, you should know where is the electric field present. So that's why I am writing that expression. So that is one thing. Second thing is how to rewrite this Q. So Q can be rewritten as the charge density multiplied by the volume, because from the beginning of the electrostatics we are seeing charge density multiplied by volume. That gives you the Q, and then the rest of the thing is same thing, E dot V. So you can easily understand. Now what happens is we would like to know how to simplify this, and then for that you can see this particular diagram. Whenever you are going to have a collection of charges, so this collection of charges is what is known as the rho charge density. And when the charge density starts to move with a speed v, so this entire thing is moving, moves together. That's what I've written. The entire charge collection, that is called charge density, when it moves together with some velocity v, then such a thing is what we call by the name current density. So what is current density means? Current density is the movement of a collection of charges with a particular speed. So therefore, once you understand this, once you are able to visualize this, we can therefore write down a proper equation which is quite familiar to you, namely that rho times v will be equal to j. So this is the meaning. When the charge density is moving with a velocity, we call it by the name current density. So now you see in this expression you have a rho here, and then there is a v here. So this rho and v can be multiplied, and we can say that this quantity is j. But anyway, there is a dot product is there, so we don't have to worry anything now. We only have to put a j here because rho will be multiplied here. So that is what we are going to write down, and therefore ultimately we are going to have E vector, then we have dot j vector d omega, and on the left hand side we have dw by dt. So now it is quite clear, right? We have been discussing, or we asked the question whether really work done kind of situation is there in electromagnetics. That was the question that we asked, and now it is quite clear that in the case of the electromagnetic system, using the appropriate equation, namely the Lorentz force law, we are now able to observe that the work done per unit time, or we say energy per unit time, is given by the integral of the electric field dot the current density present in the system in some region of space. So this is what we have seen based on the dimensional analysis quickly within 2-3 steps, okay, without knowing anything about the Lorentz force law or whatever it is. But however, this gives you a clear proof that this expression is a valid expression, and from the dimensional analysis we feel it more comfortable for the understanding. So once these things are clear, the next step is that we are interested to use this particular expression in order to understand the energy propagation. So that is the point that I would like to write down. The purpose of this equation is that using this particular equation, we will discuss and derive the Poynting theorem. Okay, we are going to discuss, and of course we are going to derive the Poynting theorem. And what is this Poynting theorem? Is actually it is talking about the electromagnetic wave propagation. It's a kind of conservation law. Poynting theorem is going to be a conservation law, and it is going to speak about the energy transported per unit time, okay, from one place. So when energy is transported from one place, in that place nothing will be there, isn't it? So that is the point that you remember from the bulb example, or that I have shown a kind of sphere and then darkness comes into picture in the middle. That is the point. So that kind of information will be mathematically derived in the Poynting theorem. So we will discuss about this Poynting theorem in the next class.